All right, now we will talk about a lemma which allows us to find some good subspace with respect to the finitely many given subspaces. Okay, so for subspaces U1, U2, Um of a vector space W over a field F, we say a subspace V of W is in general position with respect to all of them if, okay, so I forgot to say the dimension. All right, of dimension n minus t. Yeah, so W has dimension n. So V has dimension t less than dimension of W. Okay. Then we say this is the case if the dimension of UI is also decreased by t. Oh, UI intersection V. It's also decreased by t for all I. But of course, if dimension of UI is too small, then you can never decrease to negative numbers. So I should say this. All right. So we want to find the subspace of W whose dimension is n minus t. So we reduce the whole space dimension by t. And while doing so, we also reduce all the subspaces U1 up to UM. We want to reduce them to reduce their dimension by t as well. Right? And this is not, in general, this is not possible, right? Sometimes there's no subspace in general position with given list of subspaces, but as long as F is big, so the goal of the section is if F is big, then there is one subspace like that. And to do that, we're going to use a lemma called the sparse zero lemma. But before then, let me state the theorem that we're going to prove in this section. So existence of a subspace in general position right? So let S be an integer from 0 to n. So given a list of subspaces U1, U2, Um of a vector space W of dimension n over a field F, there is an S-dimensional subspace V in general position it with respect to U1 up to UM. And this is not always possible, but this is only when the size of F is bigger than S times M. All right, so that's the theorem. And to do that, we use the parallel lemma, sometimes called the Schwarz-Zipfel lemma, sometimes called the de Mello-Lipton-Schwarz-Zipfel lemma. Anyway, in the textbook it says de Mello-Lipton-Schwarz-Zipfel. I used to learn it as a Schwarz-Zipfel lemma, but anyway, so sparse. Let me call it sparse lemma. Okay, so Zipfel is 1980. Right. So let's say you have a polynomial with n variables, and it's a non-zero polynomial. Non-zero polynomial of degree d, and omega be a finite set whose size is n. Then the number of tuples upon tuples in this set omega to the n with f of alpha 1, alpha 2, alpha n 0 is at most d times n to the n minus 1. So in other words, if we take alpha I uniformly at random, right? So if we choose alpha I as an element in omega with the same with the uniform distribution, then the probability that this term becomes 0 is at most d over n, because there are n to the small n possible values, and out of them the number of solution is d times n to the n minus 1, so when you multiply it, it's d over n. Okay, so that's the lemma that we're gonna prove, and the proof is easy induction. So induction on n, the number of variables. If n is 1, then f has how many? F has at most d roots, right? If n is 1, you have only one variables of degree d. Right, and then it's trivial, right? You have only one variable of degree d, and it's non-zero polynomial, so the number of roots is at most d, and there are n possible values, so the probability that when you select its root is at most d over n. Now let us assume n is bigger than 1. Okay, so we write f of x1 up to xn as, now as a linear combination of I mean, as a polynomial of x n, right? So where gi is a polynomial with n minus 1 variables, and degree of gi is at most d minus I, right? Because the whole thing has degree d, so gi cannot have a degree more than d minus I. All right. Now let's count the roots. Okay. So how many? So the number of roots of f of x1, xn. How do we count? Okay. Right. Now let's consider the value of gk alpha 1 alpha n minus 1. So number of these tuples with gk alpha 1 up to alpha n minus 1 is 0 is at most. So this is by induction. This is by so degree of this is at most d minus k, and number of possible values is capital N, and the number of variables is, so this is n to the n d minus k to the n minus 1, right? So the number of alpha 1 up to alpha n with gk alpha 1 up to alpha n minus 1 is 0, and f alpha 1 alpha n is 0 is at most d minus k n to the n minus 1, and trivially I just multiply n, right? So this is d minus k times n to the n. Oh, something's wrong. This is n minus 2, n minus 2, so n minus 1. And so this is the first case. The second case is when this leading coefficient is non-zero, and number of tuples is at most n to the n minus 1, trivially. And then for each of them, there are d many ways to select alpha n, right? There are at most d choices of alpha n for each of them, so that f of alpha 1 up to alpha n is 0, right? Because this is a polynomial. So the number of them, so number of alpha 1 up to alpha n with the f of alpha 1 up to alpha n is 0, and gk is non-zero, is at most oh, what is the degree, by the way? This is the degree is at most k, right? So degree of this polynomial is k. I mean, when you fix alpha 1 up to alpha n minus 1, so it's k times n to the n minus 1, right? I'm multiplying this k together with this number. So now this implies that the total number of alpha 1 of alpha n such that f of alpha 1 of alpha n is 0 is at most k times n to the n minus 1 plus d minus chi times n to the n minus 1, so which is d times n to the small n minus 1, right? So this proves the lemma, the sparse zero lemma. All right, now we are ready to prove our main theorem. Theorem on the existence of subspace in general. In general position. So we're given these subspaces u1 up to um, and if some subspace ui has dimension less than t, okay, so what is t? So let t be the m minus s. So I want to reduce the dimension by t. If there is a subspace ui whose dimension is less than t, then we could, what we aim is to make this subspace become a zero-dimensional subspace. And it doesn't matter if we increase subspace dimension of the ui to t, right? If it's true for a slightly bigger subspace, so if I can find the superspace of ui, which still has dimension at most t, and after taking intersection with the v, it becomes dimension 0, then the subspace ui also becomes dimension 0. So we may assume dimension of ui is at least t by enlarging ui whenever dimension of ui is less than t, right? So add more vectors. Now our goal, let me remind you the goal, find the subspace v such that dimension of ui is intersection v is dimension of ui minus t, and dimension of v is n minus t. All right. Now what we're gonna do is construct some polynomial. All right. So we fix a basis w, and then each vector of w is represented by these spaces. Now let's consider the following polynomial. So let pi x1 x2 xn minus t is the determinant now. Each column, right? So let's say w, the basis of w is w1 up to wn. Now here I'm gonna put w1, w2. Okay, let me draw again. w1, w2, wt. So that means here we put first t vectors Oh no, actually, no. What's t vectors of the? Yes, this is for I, not W1. Okay, W1, I. So put t vectors of basis of UI. Remember, UI has dimension at least t, so I can choose t vectors inside UI. And then here we put the x1, x2, xm minus t. All right, so the number of rows is n, number of columns is n. Right. So where xi is a vector in f to the n. No, I shouldn't say xi. X1, x2, xm minus t are vectors in f to the n. So in other words, pi, you can think of pi as a polynomial in x11, x12, x1n, x21, x22, x2n, xm minus t1, xm minus t2, xm minus tn. All right, so the number of variables is m minus t times n. And what is the degree of pi? Well, in the degree, we're gonna multiply variables here in one from each column, and these are constant. Everything here is constant, so degree is just the number of columns having at least one variable. So this is m minus t. All right, now let X be a vector space spanned by x1, x2, xm minus t. So if pi, this determinant, is non-zero, then determinant of ui plus x is n, right? Because I take the first t vectors from ui and take x. All these things are linearly independent, so they span everything. So then dimension of ui intersection x is going to be dimension of ui plus dimension of x minus dimension of ui plus x, and dimension of x is of course n minus t, so dimension of ui plus n minus t minus n, so this is going to be ui minus t, right? So the goal is to find x1, x2, xt, no, n minus t, so that pi x1, x2, xm minus t is non-zero for all I. Right? How do we ensure that? Well, let g be the polynomial obtained by multiplying all these things. Then degree of g is what? It's m times degree of each of them, right? So degree of g is m times s. Now it's time to use the previous theorem. So number of roots of G is at most right degree is ms, and the cardinality of the field is the size of f, and number of variables. Number of variables is so n minus t times n. That's the number of variables. So now so that means what we want is if number of all possible values, so that's this, right? This is number of ways to assign values to these variables x11, x12 up to x n minus t n. If this is strictly bigger than this is minus 1, then we are done, right? Then there is an assignment x1, x2, xn minus t in f to the n such that g of x1 up to xn minus t is not 0. And if you look at this condition, that is the same as saying size of f is bigger than m times s. All right. So that's it. Here we take omega to be the set of all possible values in the field. So omega is equal to the size of f. Omega is equal to f. All right. So this is a theorem about reducing the whole dimension of the whole space so that every subspace that I'm interested would have a smaller dimension. Now let's do the opposite. Now I want to reduce the whole space while keeping every subspace that I'm interested will still have the same dimension as a corollary. So that's a different direction, right? So let t be a non-negative integer, and that u1, u2, um be subspaces of a vector space W over a field F, and dimension of W is n. Now what we want to do is find the linear transformation. There is a linear transformation phi from with W to W prime such that dimension of W prime is n minus dimension is t, and dimension of phi of ui, so the image has dimension reduced by not reduced, same, but it's possible that dimension of UI could be bigger than t, then there's no way to keep it, so we take a minimum. This is when size of field is bigger than m times m minus t. And if this is the case, we say such a linear transformation is in general position with respect to u1, u2, um. So let's see why this is true. So what we do is let V be a subspace of dimension n minus t all right, n minus t dimensional subspace of W in general position with u1 up to um. And such a thing exists because size of field is bigger than m times m minus t. So if you put m minus t as s, then you get such a thing. All right. Yep. Now, such a subspace V exists. Okay, take any linear transformation phi from, let's say, W to W. The image doesn't matter, but such that the kernel is equal to V. Such a thing exists, right? Because you take, for instance, you take a basis of you take a basis of V and then extend it to a basis of W and construct a linear transformation where all the basis vectors inside W will be mapped to 0 and outside is mapped to identity. Then when you end up is a linear transformation where the kernel is exactly V. Right? So what is the dimension of the image? Well, it's the dimension of this UI minus dimension of UI intersection kernel. Right. And right, so what's the dimension of the image when I send the UI? Well, anything inside the kernel will be collapsed, right? So everything outside will survive and the dimension is decreased by that. So this is dimension of UI minus the maximum of dimension of UI minus t and 0. And this is equal to minimum of t and dimension of UI. All right, so that's the linear transformation. All right, now we are ready to prove the two families theorem. Of Lobas. Right, so we're going to prove this theorem. So it's enough to reduce the whole space to W. So how do we prove? So we may assume F is big by taking what? I mean, it may be possible that F could be small, but we take the extension field. Field of F, right? So just replace F by like polynomials. Polynomials over F, and it's extension field. Right? So you can assume that the field is big enough so that you can apply Schwarzschild lemma. Now it's enough to find. I mean, okay. Let's assume we may enough to take in. It's enough to consider the case that dimension of W is bigger than R plus S, because we did the case when dimension is equal to R plus S, right? In this case we are done, so what's left is this case. Now by the previous corollary, there is a linear transformation by, in general, position with u1 up to u m. Oh, not u1 up to un. Let's say I need to fix it, right? So u1 plus v1, u2 plus v2, um plus vm. No, actually, I want to say more. It's better to keep all the sums. So let's say ui plus vj. Okay, that would be for all ij. Such that dimension of, right? So w to w prime. So w prime is the image of w, and dimension of w prime is equal to dimension of, I want the image to have a dimension R plus S, and right, so we are reducing the dimension by something, right? So here, so when you apply the lemma, this t becomes R plus S. And dimension of the image of ui plus vj becomes dimension of, okay, so minimum dimension of ui plus vj comma R plus S. Now let's look at, previously ui has dimension R and vj has dimension S. So their sum has dimension at most R plus S anyway. So this is equal to dimension of ui plus vj. All right. Now, why is this useful? Now let's compute this thing. So what is the intersection of image of ui and image of uj? Right, for I less than equal to j, this is dimension of image of ui plus dimension of image of vj minus dimension of image of ui plus vj. And by the way, this image stays same, so that means dimension of image of ui is still the dimension of ui, right? Because over the ui plus vj, this linear transformation is injective. So this is equal to dimension of ui plus dimension of vj minus dimension of, now by the assumption this is ui plus vj, so this is becoming ui intersection vj. So nothing changes between the ui and vj, right? The intersection patterns are same. Now we solve the phi u1, phi um, and phi v1, phi vm are subspaces of phi w where all conditions are satisfied, right? Phi ui intersection phi vj okay, let me copy from the left hand side, right? Phi ui intersection phi vi is 0 or I, and phi of w has dimension r plus s, and dimension of phi ui has r, dimension of phi vj is s. So this implies that number of them is the most dimension of this, right? And this is equal to r plus s choose r. All right, so that's it.